Hi folks, and welcome to our evening session on trig functions, and we're going to be focusing for the most part on the unit circle and kind of build to all the other concepts from there. So I figured a good place for us to start is that unit circle. So without further ado, let's get started. So what is the unit circle? Well, you actually learned that in college algebra, hopefully. It's a circle such that x squared plus y squared equals 1. So if you take a look at the circle here, we have 1 sitting right there, and you have 1 sitting right there. But notice you also have -1 right there and -1 down below. So you have coordinates. I mean, we have 1, 0, 0, 1, -1, 0, and 0, -1, all appearing on our graph. There's some special side notes with this unit circle that really are important in mathematics. They actually go all the way through into the upper level material. So you'll see it all the way through the calc sequence, all through calc 3. This comes in handy quite a bit. So the facts that we use over and over again is that x equals cosine of theta and y equals sine of theta. Now you might be asking, what is theta? Where the heck does that come into play? Well, theta, we start with this value right here, and we'll call that 0 radians, and then we keep on rotating in this fashion, and then we have angles like theta. Okay, so when we get up to this top coordinate, you get pi over 2 radians, and hopefully you all can see that right there. So we have pi over 2 radians on the top, and then we have over on the left hand side along there, it's pi radians. So if I go, just a little FYI, that angle from our beginning angle right there to all the way to this negative x-axis, you'll get pi radians sitting right there. So this is pi radians. That's all I'm labeling there. And so you can go on to the bottom and you get 3 pi over 2, and then you go on over back to the beginning, you get 2 pi, and we can continue this trend. So pi over 2, we add another 2 pi to it. So if I take pi over 2 plus 2 pi, that's going to be 5 pi over 2. And if I take pi and add 2 pi to it, I'll get 3 pi and 3 pi over 2. I can add 2 pi to it, which would be 7 pi over 2. Basically just making a full circle there. And I can continue this fashion over and over again. I can also go in the negative direction. So negative direction, if we're going counterclockwise for the positive, that means clockwise would be the negative. So I could say -2 pi is right here. That means this would be negative pi over 2 because I subtract 2 pi from 3 pi over 2. The same thing over here, you get negative pi. In this case, you'd get negative 3 pi over 2. And we can continue forever and ever, however many times we want to go around the circle. It's just some multiple of 2 pi, essentially, times an integer. So now, a lot of people might be more comfortable with degrees. And so you got to remember there's 360 degrees in a full circle. So you go 0, then it goes 90, 180, 270, then 360. So where you're seeing that line up, that's the magical numbers in terms of degrees. If you have trouble with that, please let me know. I'm happy to answer that question along the way. So, but for the most part, we try and work with this in radians, and it's more beneficial to be in radians, even though degrees might be a better, more comfortable, I should say, sort of notation. So at the end of the day, now what does this tell us? Okay, well, it gives us all sorts of information. Let me go with green here. So think of the coordinates of this point on the unit circle. Okay, so notice we're in between, and the usual angles we'd work with is just 0 and pi over 2. So I'll focus on 0 and pi over 2, and we can think of what quadrant we're in. We're in quadrant 1. Okay, so let's look at the coordinates of this point. Well, what is your x value? Well, your x value is going to be something like this, and your y value is going to be something like this. Okay, but in either case, notice both of those values are positive. So you get a positive and a positive. And so what is the sine of theta? Well, you have these distances here. we have a hypotenuse, and what would the hypotenuse be? Anyone want to take a stab at what the hypotenuse might be on this particular triangle? So what's the hypotenuse if I were to draw out this triangle right here? Any guesses? And so it may be tricky at first, but at the end of the day, when you look at that, you're talking about x squared plus y squared equals 1. So that means the radius at all times, the radius of this circle, is always equal to 1. So in fact, every single value that we're looking at, we're going to have 1 as the hypotenuse. So this is the hypotenuse. Right? And so that's why we get away with, notice I said sine of theta would just equal y. Well, it's just the y value over 1, and so we're left with, and the reason why it's y, because that's the height of this triangle. So it's just the y value, and notice our y value is positive in this quadrant. Okay, so we'll have a positive sine of theta. Let's look at the cosine theta. Well, that should just be the x value, and notice our x value is positive in this quadrant. So, and the reason why it's the x value, it's x over 1. So you get a positive sitting right here. Okay. Well, tangent theta. Here's where we can break down our trig functions. Now, a lot of people like adjacent over, so you have adjacent, opposite, and hypotenuse all involved with all the triangles, and people like to work with that. I would highly recommend using sines and cosines for all the rest. So tangent theta is just sine of theta over cosine theta, which in this case that would be the y value over the x value, right? According to this, because the sine of theta is y, the cosine theta is x. If you look at cotangent theta, easy way to think of that, that's just 1 over tangent theta, or it just reverses the order of the tangent theta. So cosine theta over sine of theta is what we're left with there. So that means that's x over y. In the other side of things, if we have secant theta, that's just going to be 1 over cosine theta. Sorry, I almost said cosecant for some reason. So that's just 1 over x, essentially, where I'm referring to the x up above. So don't get confused later on. We're going to be solving for x and things of that nature. And then last but certainly not least, cosecant theta, that's 1 over sine of theta. And so this is the beauty of the unit circle. Everything can boil down to just the sine and cosine. As soon as you determine those, you can determine the rest. Now sometimes people might give you the tangent theta or give you the secant theta, and then you got to figure it out from there. But at the end of the day, we can work with this. So notice all the x values and y values are positive. So this, in quadrant 1, things are easy. If everything's positive, life is good. So positive, 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 and positive. Okay, so that's the first scenario. Now let's go to another scenario. We'll draw with this light blue here. Let's say we had an angle theta. And by the way, if you have any questions at any point in time, please ask. That's what I'm here for. That's the main point of this. So notice, if we hit the circle in this, and this is our new theta value, what do we have? Well, we have, in this case, think of our x value. Well, our x value lines up over here. That's close to -1. It's actually a negative value of some sort. That's all we care about. And then our y value is still, so our y value would land right up here in this case. So it's positive. And that happens for everything in this quadrant. What quadrant is this? This is quadrant 2. Okay? So in quadrant 2, we have a negative for the x and a positive for the y. So what does that mean? Well, sine of theta is just the y value, so that's got to be a positive. Right? So cosine theta is the x value, so that's going to be a negative. Now from here on out, it's pretty easy as long as you use your little properties. Right, so we have properties here, and we have some properties there. Okay? So moving forward in this condition, so tangent theta, that's y over x, that's a positive, or yeah, a positive divided by a negative, that's going to be a negative. Our secant theta, what is that? Well, that's 1 over x. Well, our x value is negative, so that's going to be a negative. Our cosecant theta, well, that's 1 over y. Our y value is positive, so this thing is positive. And then cotangent theta, notice that's x over y, so you have a negative divided by a positive, that's going to be negative. Okay? And quadrant 2 is done. So we can keep on moving forward. We'll do orange for the next one. So say we have a new angle, and our new angle stops right here. And it goes on down, and this is our new, well, don't let your eyes fool you, that's a straight line. I'm trying to draw. That's our new theta. Okay, well let's look. If we have coordinates here, notice this is going to be a negative and a negative. Okay? So everything's negative, so that means sine of theta, well, everything in terms of the sine and cosine. So sine is negative, cosine is negative, but notice tangent is just y over x, so you have a negative divided by a negative, that makes it positive. In a similar manner, cotangent is a negative over negative, so that also is a positive. So I'm jumping around a little bit, but just to make sure we can see that right away. The others just have one x value or one y value, so that means the other two coordinates are going to be a negative value in those cases. So at the end of the day, when we're in quadrant 3, and that's, sorry, I wrote the angle there and started filling in. I didn't write where the quadrant was. Quadrant 3, we have negative, negative for the sine and cosine. Tangent and cotangent are the only positive values, and then secant and cosecant are back to the negative. So last but certainly not least, let's take a look. Let's go with red maybe. And so in the red case, we go around, and let's say we get to here. And we get a value right there. Well, notice we're in quadrant 4. And this angle would be theta now. And our x value is positive, our y value is negative. Okay? So, moving forward from here, positive, negative. Okay, let's see what happens. So our sine of theta is just our y value. Our y value is negative, so this is negative right here. Okay? And cosine is our x is positive, so we get this value right here. And then we have tangent theta. That's going to be y over x, so you get a negative over a positive, which makes a negative. Secant theta should be 1 over x, so that's just 1 over a positive. That's going to be a positive. And notice every time, by the way, if you look at the cosine theta and the secant theta, they always match. And there's good reason, because secant theta is just 1 over cosine theta. So in terms of the sign of it, that's how you get that answer right away. Cosecant theta is 1 over y, and our y value is negative, so we'll get negative. And so similarly, you have cosecant theta and sine of theta. They're always going to match in terms of the signs of those things. So last but not least, the cotangent. Notice you have a positive and a negative involved, so that means we're going to have a negative when we divide those two. So you might be asking, why the heck do we make the chart? Well, we can make things easy. So say you have, so question. Let's see here. So let's say our question gave us something along the lines of tangent theta greater than 0, and then cosecant theta less than 0. And the problem asks, what quadrant are you in? So we look for tangent theta. Let me get the black piece on here. Tangent theta greater than 0. That means tangent is positive, right? So the two places tangent are positive. I go into my chart and I see two places where tangent is positive. Now of those two, all I need to look is when cosecant theta is negative. So cosecant theta is negative right there, and so that means we are in quadrant 3. It's as simple as that. So if you have the chart, right, you can cut this down drastically, and it's going to help us as well when we get into these angles. What do we have? We have maybe a secant theta is negative, and we know what quadrant it is in. So what's the rest of the angles? So we're going to refer back to this quite a bit. Now I'm going to try and have you memorize it, but for right now, if you have a chance though, please write it down, make that chart, and you can reference it for the rest of this video at least. Okay, so take the time, write this thing down. Just the pluses and minuses can do wonders in terms of you actually being able to solve these things. So let's get down to it, and we're going to work quite a bit. So we have the point square root of 2 over 2 negative square root of 2 over 2 is on the unit circle on the terminal point of the angle theta, right? So first off, I got to draw this shindig. Okay, so notice that's positive, and I'm not saying this is going to be perfect. Let's just say we have a unit circle. I'm not saying this is to scale whatsoever. Well, look at that. That's the most beautiful circle you've ever seen, I'm sure of it. So now, what are we looking at? Well, let's take the blue here. We have some angle, and we're going to have square root of 2 over 2, negative square root of 2 over 2, so it'd be kind of like right in the middle. So we have something like this. And so we have something that goes like that, and that's our angle theta. Okay? So now, it is the unit circle, so this is going to be 1. And remember, our x value is equal to cosine of theta. Our y value equals sine of theta. And this wants us to determine all 6 trig functions. Well, this is going to be pretty easy when it comes down to it in terms of those first two. Because and remember, just as in the last scenario, you have x squared plus y squared equals 1. Okay, so you have cosine theta. That should be just x. It's the x coordinate, which is equal to square root of 2 over 2. Done. That's all it is. All we did was pull that x value right there. Any questions on that piece? Okay, sine of theta. Right? And yes, you can think of these in terms of cosine theta is adjacent, so you might know so kotoa, so meaning opposite, sine is opposite over hypotenuse. Cosine would be the ka, and then that's cosine theta equals adjacent over hypotenuse, and then toa, meaning tangent theta, equals opposite over adjacent. I'd recommend, though, if you're really wanting to get good at these reference angles and all sorts of stuff, and working with the unit circle, this is probably going to benefit you more. If you get sine and cosine as terms of x and y, then know the rest of them in terms of just sine and cosine. So tangent theta equals sine of theta over cosine theta. Now granted, you could write that as y over x, as it works just as well, but at the end of the day, what happens? Well, we have this as negative square root of 2 over 2 divided by square root of 2 over 2. Oops, over 2. It's not supposed to be a square root of 2. Well, look at that. Those two numbers are pretty much the same with the exception of that negative symbol up top. So that means this is just negative 1. And in fact, we can be pretty precise in terms of what angle this is in just a little bit. And I'll explain how we could do that. So moving forward from there, you can go to secant theta if you'd like. I forget which order we did them on the other side. So this would be 1 over cosine theta. So notice that's 1 over, well, what's the cosine theta? That's square root of 2 over 2. So that equals 2 over the square root of 2. And if you wanted to rationalize the denominator, you can make it 2 square root of 2 over square root of 2 times square root of 2, which is just 2 on the bottom. So those 2 will cancel off with that, and so you're left with just square root of 2. Right. To be honest with you, I'd be fine with the 2 over square root of 2, but just in case it's having you simplify or something like that. But if you're punching into a calculator, it's pretty straightforward in terms of those regards. Cosecant theta. What do we have going on here? Well, cosecant theta is just 1 over sine theta. So notice we're just putting everything in terms of sine and cosine. It's so much easier for us as long as you know your unit circle well. Because as soon as you have that, the rest kind of falls apart right away. So now you have 1 over the negative square root of 2 over 2. And notice the only thing we flipped with the previous one is just the fact that you have a negative symbol. And so this is just negative square root of 2 if you simplify. And you can go through those steps. If you want to see them, let me know. I'm happy to go through them too. And last but not least is cotangent theta. A couple ways you can do this. So one, you can do cosine theta over sine theta. If you're good with your trig identities, though, another way you could look at it is 1 over sine theta. Or not 1 over sine theta. 1 over tangent theta. And so this is the same thing as 1 over tangent theta. But I can use the other and still derive the same answer. The reason why I'm saying 1 over tangent theta, because we found tangent theta to be pretty simple. It's -1, so this whole thing is just -1. Okay, so we found all the angles. Now, this is not part of this, but let's say we wanted to find what theta is. So what does theta equal? So what is theta? Well, let's think about this. Okay, so we have basically these two sides are the same length. Okay, so now you might think, okay, what would be this angle when we talk about the length of those two sides? Well, you're talking 45 degrees. Okay, the reason why, and if you go back to your triangles, so if I have this side being A and this side being A, and notice this side would be technically, you add both of those after you square them and you take the square root, so this is going to be square root of 2A squared, which equals the same thing as 2 times the square root of 2 times A, because A is some distance. So what does that mean? Well, that means this angle and this angle must be the same. Okay, and so that means that you have a 45 degree angle and a 45 degree angle here. Right? So you might not know right off the gate what 45 degrees is. Well, we can fix that real quick. So 45 degrees times pi radians is equivalent to 180 degrees, right? So the degrees will cancel and we're left with pi over 4, because 45 and 180 they're kind of in common with 4 times 45 makes 180. So you have pi over 4 radians sitting right there. Okay, we know that this is while 0, so you could say negative pi over 4, right? But the best way to probably write it, what is theta? You could write negative pi over 4, but if we add 2 pi to it, oops, negative pi over 4 plus 2 pi, that's going to be a little bit better answer. So notice that's 8 pi over 4 and negative pi over 4. If you add those two together, you get 7 pi over 4, right? And so the best way, as drawn, it's 7 pi over 4. But other answers that are feasible, you could say 7 pi over 4 plus some 2 pi k, where k is an integer. What does that mean? Well, you can start with counting numbers, so things like 1, 2, 3, 4, so on and so forth, because you're just making circles around that point over and over again. And then you can also toss in -1, -2, -3, -4, meaning you're going counterclockwise a full circle. Or you can plug in 0 and just end back up at 7 pi over 4. That's the most general answer for this thing. Okay, but 7 pi over 4 would work. Not a part of this problem, but just so we know what's happening. This will come in handy later when we start talking about inverse trig functions. Alright, moving forward. I don't see any questions thus far, so let's keep on rocking and rolling. So we have suppose that secant of t equals -2 and lies in quadrant 2. Find the 5 remaining trig values and list the values of the angle that could correspond to t. Alright, so let's say we have our this is no longer a unit circle, I wouldn't think, so not quite sure what the value is of the circle, but we know it lies in quadrant 2, so you have something along here, and we have t going on right there. Still, you'll have pi over 2 on your circle, 0 over here, 2 pi. You'll get 3 pi over 2 down below, things like that. And we know that secant of t equals -2. So let's not worry about the negative just yet. Let's just make a triangle such that this happens. Well, if we make a triangle that this happens, remember, this means 1 over cosine of t equals -2. Actually, we can kind of solve real quick for one of them. So from that, just that point right there, if 1 over cosine of t equals -2, multiply both sides by cosine t, you get 1 equals -2 cosine t, and now divide both sides by -2. We get our first value really quick. Cosine of t equals -1/2. Okay, so now we have a triangle that we can kind of work with. So that's adjacent over hypotenuse. So if we have a 2 right here and we have a 1 right here, and technically it's a -1, but I'll leave the -1, we'll put that part right there. So now we need that y value. What's the corresponding y? So the way to figure this out, we use Pythagorean theorem. Oh, and by the way, we have theta right there. So moving forward from this part, notice this is, Pythagorean theorem says a squared plus b squared equals c squared, right? So our a is 1, so you get 1 squared plus b squared equals 2 squared. So b squared, so that's 4 minus 1 is 3, equals 3. And usually you need a plus or minus, but since we're talking distance, we'll just put square root of 3 for right now. But that means that's our height, so this is square root of 3. I know this isn't drawn to scale. As soon as we have that, so we have the coordinates of that point, it's -1 square root of 3. And then this distance is 2 for our radius. So we have our full triangle right there. Okay, so now we're ready to rock and roll and get down to business. So we have cosine of t equals -1/2. That means sine of t, notice that's our y value. We no longer have a radius of 1, so it's a little bit trickier, but still not so bad. We're talking square root of 3 for that, and then we go over 2. Now, let's say we were worried about positives, negatives, and all that jazz. Let's go back 2 slides here, or whatever you want to call this thing. Okay, so I have, what was it? Sine was positive, cosine was negative in quadrant 2. So I can basically do the rest. I don't even need to worry about the pluses or minuses. I can just draw that triangle, and then I can go back to my chart to get all the pluses and minuses in order. So that's why I say use this chart over and over again. As soon as you know what quadrant it was, we knew what all these things should lie, what they should be. Okay, so keep that in mind. Know that chart well. So now moving forward, we have tangent of t, and so we can do, just to kind of keep in the same vein as before, you could do opposite over adjacent using this triangle and be done in a matter of seconds. That's fine. If not, we can do sine of t over cosine of t. Sine of t, we have that's square root of 3 over 2. Cosine of t is -1/2. Notice the 2's will cancel with each other, so you're left with just negative from the -1/2, and then you have a square root of 3. And we had negative before on that tangent value. So now secant we already have, don't need that anymore. cosecant. This one's pretty easy. You just flip the sign. So 1 over sine of t. So that makes 1 over the square root of 3 over 2. So that's 2 over square root of 3. If we want to get fancy with it, we can multiply both numerator and denominator by square root of 3. So this is 2 square root of 3 over 3 is the same thing. Last but not least, you go cotangent of t. You can do cosine of t over sine of t. I'm going to cut out this time and go 1 over tangent t just to make life easy. Since tangent t is negative square root of 3, this is 1 over negative square root of 3. So you can multiply both numerator and denominator by square root of 3. You get negative square root of 3 all over 3. Okay, and then we want to find the values of the angle that it could be if it's in quadrant 2. So notice that means this angle, so we have a square root of 3 on this side, a 1 on this side. So if we did our little reference angle right here, what would that be? Well, think about that. You have a 30, 60, 90 triangle, but which side is going on this? Well, it has to be a 60 degree, okay, if you recall. Okay, so 30, 60, 90 triangle, so this is 60 degrees because the larger side is over here, and this is 30 degrees. So 30, 60, 90. Now, let's think about that. So let's convert 60 degrees first off. Well, yeah, we can do this a couple ways. Let's take 60 degrees and let's turn it into radians. So that's pi radians over 180 degrees. Or if you like, I mean, some people prefer the 2 pi being 360 degrees. That works out the same. It just reduces to pi radians over 180 degrees. So notice the 60 and 180 cancel. This is pi over 3 radians. But notice that's the reference angle. So this is a reference angle. So if we want t, so t should equal pi minus, right, because we go all the way to pi and we subtract off that 60 degree angle. So pi minus pi over 3, which is equal to 2 pi over 3. Okay, so that's one possible answer, but we can move forward from there. Actually, we can get a lot more. So you could also say, remember, we can keep on going around the circle. So I could do t to be that angle, but I could also add in an extra loop around and go right back there. So what we say is this is 2 pi over 3 plus 2 pi k, where k is an integer. If you'd like to see a few more values, I can toss them out there. It's not too hard. So you can add another 2 pi. So notice that would be 6 pi over 3, which means this would be 8 pi over 3 is another possible value. You could subtract 2 pi, which would be subtracting 6 pi over 3. So that would be negative 4 pi over 3 would be another value. And you can keep on going. There's infinitely many values. Just you can go however many times around a circle back to that reference angle of t, or that the reference angle of 60 degrees from the pi. And you're good to go. So, any questions on that piece? Please let me know. As I said, there's a chat box over there, so I'm happy to answer questions. I know some of this stuff can be tricky. But you can see we all kind of boil back down to that original unit circle that we were talking about. So now, on a circle with radius 14 feet, what angle in degrees would subtend an arc having a length of 21 feet? Don't let your eyes fool you, that is feet right there. So the circle business, if I have a circle here, pretend that's the center of the circle. If I have r here and I have theta here, if this, let me color it something different. So if this part of the circle is what we're looking for, and let's call that s, S equals r times theta, but there's one caveat where theta is in radians. That's the tricky part for a lot of people. They forget that it has to be in radians. But once you have that, life is good. So now let's work with this. So you have 21 feet for the length of the arc, so that means S, that's 21 feet. R is 14 feet, and then we have theta. Okay, so theta equals 21 over 14, or better yet, you get theta equals, both of those have a factor of 7, so this is 3/2. And I'll put radians for right now, but we want in degrees. So theta equals, the way we take care of that, we have 3/2 radians. Now we want to cancel off the radians, so which one goes on top? Well, it's 180 degrees is pi radians. So now your radians can cancel. That's the whole idea there. So radians cancel. Notice that's not going to be too bad. So you have 180, that makes, divided by 2 is 90, times 3 is 270. So this equals 270 degrees. Hey, what do you know? So my sector of my circle wasn't drawn to scale, but that gives you an idea. We have 270 degrees, good to go. Questions on that? Okie dokie. So let's find the arc length along a circle of radius 10 meters subtended by an angle of 240 degrees. So how the heck do we do this? Well, once again, we're going to use S equals R theta. So R is pretty straightforward. You get 10. But now theta, we need to convert degrees to radians. So you have 240 degrees, that's pi radians over 180 degrees. Okay, so what do both of those have? A common factor of 60, I believe. So that's, the degrees would cancel, and so you're left with 4 over 3 radians. And double check me, I'm doing this all in my head, so bear with me now. So this is 10 times, yeah, definitely double check me. I forgot the pi, 4 pi over 3. So 10 times 4 pi over 3, so this is going to be 40 pi over 3 meters. And if it asks you to like punch into a calculator or something, you can bring up your calculator if you don't already know. Oh, come on. There we go. Okay, so you can type in 40, and then you click the, I think it's the second button right there. Okay, yeah. Second, and then here's the pi right above the caret. 40 pi divided by 3, and you can get an answer, an approximation. So we get however many decimal places you need. We'll say 41.888. Okay. If there's any questions on that, please let me know. All right. So our next one, use reference angles to evaluate all trigonometric functions associated with the angle theta equals 7 pi over 4. Wowzers, right? So where the heck does that thing land? So first off, I mean, we can make our unit circle, or we can make any darn circle that we please. So remember though, we have 0, pi over 2, pi, 3 pi over 2, and 2 pi. Now, this might be hard because we have 7 pi over 4. Well, there's a quick fix for that, and that's what I'm going to do right here in blue. Just multiply, if you have a denominator, multiply that denominator and numerator by the same number to get you to 4. If you don't, just multiply things by 4 over 4. Okay, so this thing equals, well, if we look at it, that's 2 pi over 4. 2 pi equals 8 pi over 4. Pi equals 4 pi over 4. And 3 pi over 2 equals 6 pi over 4. So now we have a pretty good gauge as to where 7 pi over 4 fits. It has to fit right smack dab in the middle of these two. Okay, and so this would be 7 pi over 4. All right, so we're in good shape. So how much more do we need in order to get to here? Well, it doesn't take much to realize that's going to be pi over 4. Well, if we have pi over 4, hopefully you're getting good at radians. We already talked about this one. So let's talk about this here in just a second. If I have pi over 4 and another pi over 4 right here, because this is 45, 45, that means a couple different ways you can look at this. You can make it a unit circle if you want. What I'd recommend, though, is just going 1, 1, square root of 2, right? Because it's a common triangle that we know. Now, the only thing we have to realize is sine is negative. So sine of and so the rest, cosine of 7 pi over 4 is positive because of the quadrant that we're in. Rest, just use that triangle, right? So you can start with sine of 7 pi over 4. Now, if you'd like me to rationalize these things, that's fine. I'd be honest, just having the values works great, right? So sine of 7 pi over 4. Well, notice that's going to be negative, because it says it's negative according to that table that we began with, and it's 1 over square root of 2, if you like. And another way we could write this, if it was a unit circle, we could write it as negative root 2 over 2 as our y value. Cosine of 7 pi over 4. Well, it's the same thing as a sine because it's the same angle essentially for a reference angle. Only difference is it's positive now. So this is 1 over square root of 2, which is the same thing as square root of 2 over 2. Now, I'm going to start to focus on these values, so this one and this one, to work with the rest. Okay, so if we want tangent of 7 pi over 4, well, actually, I don't even need that. On the tangent, notice sine is negative, cosine's positive, so I can go about it one way, 7 pi over 4 over cosine of 7 pi over 4. Or I could do the opposite over adjacent thing, which I have 1, and just remember it's going to be negative, so you could do it either way. I would say that way would work better in terms of being speedy, but if not, we'll go this way. Notice they're the same number, just one's negative, one's positive, so you get negative 1. Okay, that means cotangent of 7 pi over 4. The beautiful thing on this is it's just the reverse, so you'd have to flip the tangent upside down if it was a fraction, but in this case it's pretty easy because it's negative 1, so this is 1 over negative 1, so this also equals negative 1. Okay, so only a couple more. Secant of 7 pi over 4 equals the 1 over cosine of 7 pi over 4, which equals 1 over, well, cosine is 1 over square root of 2, so that's 1 over square root of 2. And so that would be just square root of 2. In terms of the cosecant, let's see if I can fit that over here. Cosecant of 7 pi over 4. Notice that's 1 over sine of 7 pi over 4. Oops, there we go. So that's 1 over negative 1 over the square root of 2, and so that is negative square root of 2 as our final answer. Okay. Any questions on that piece? If so, please, there's a chat box on the right hand side. Please feel free to just kind of chime in. I'm happy to help you out as much as possible. So we're getting the unit circle down. Let's keep on keeping on, I guess. Now, given sine of x equals 1/8, evaluate sine of negative x, cosine of negative x, tangent of negative x, secant of negative x, cosecant of negative x, and cotangent of negative x. Wowzers. So what I'm going to do first is I'm going to bring up a function here. Let's see if I can do that. Sine of negative x. Okay, so here's sine of x, and notice you don't have a perfect pattern going on here. So you just have this this oscillation up and down, I mean, when I say perfect pattern, it's not evenly distributed on both sides. So this is a special type of function. First off, it's called a periodic function. This is y equals sine x, by the way. So it's a periodic function, but it's also an odd function. What does it mean to be an odd function? Well, a function is odd if f of negative x equals negative f of x. Okay, so it kind of looks like you're being able to move that on through, but not necessarily. So in this case, we have sine of negative x. Since it's an odd function, that means we have negative sine of x. Okay, so and what's sine of x? Well, sine of x is just 1/8. So that's negative 1/8. And so that's our first answer. Okay? So now let's take a look at cosine of negative x. What the heck is that thing going to be? Well, I'll make up a new graph here real quick. Let me scroll up. Okay, so what you're seeing here, I'm going to try and graph cosine of x. And I'll just focus from negative 2 pi to positive 2 pi. And I don't need any labels or anything like that. And we'll plot our range from negative 2 to positive 2. Oh, sorry about the error. Forgot that extra little piece. Okay. So hopefully we'll be able to see this in just a second. So this is the graph of y equals cosine x. When you take a look at this, notice if I start from 0, if I go off to the right, it's the same as if I were to go off to the left in terms of the y values. Right? This is a special type of function since it's symmetric about the y-axis right there. We call that an even function. Okay, so what does that mean? Well, if we have an even function, so now what I should write up here is this is an odd function if f of negative x equals negative f of x, and then an even function occurs when you have f of negative x just equal f of positive x. Okay? So in that case, what the heck is happening here? Well, cosine of negative x should equal cosine of x. And you might say, well, that's hunky-dory, but that doesn't do jack squat for me here because I don't have a cosine. I just have sine of x. Well, that's where we go back to what's going on with this. If sine of x equals 1/8, that means our angle is x. And remember, this is opposite. Oh, I'm running out of space there, sorry. Let me do it this way. Switch colors. Opposite. And hopefully we can see that over hypotenuse. So that means the opposite side is 1. The hypotenuse is 8. So now we got to use Pythagorean theorem because it's a right triangle. So you get a squared plus b squared equals c squared. Our c is 8, so we get 8 squared. Our a, or you can call it b, it doesn't really matter, 1 squared plus b squared. So you get 64 minus 1 would be 63, so b squared equals 63. So that means this side is the square root of 63. Okay? So notice now we want cosine of x. What the heck happens? Well, you go adjacent over hypotenuse. Right? So adjacent over hypotenuse would be square root of 63 over the hypotenuse, which is 8. Done right there. So now the rest of them are just basically using the same kind of rules we used before. So let's say tangent of negative x. Well, remember, this is sine over cosine, but we got to change it to sine of negative x over cosine of negative x. Right? We already calculated the sine of negative x. That was negative 1/8. And then the cosine of negative x was square root of 63 over 8. So notice this makes the 8's cancel, and you're left with just negative 1 over the square root of 63, and you're done. Okay, in a similar manner, when we go to cotangent of negative x, that equals 1 over the tangent of negative x. Or you could do cosine of negative x over sine of negative x. That works as well. So this is 1 over this negative 1 over the square root of 63. So the negative will still stay in there, and we're left with negative square root of 63. Okay, only a couple left. You have secant of negative x. And so that whole thing equals just 1 over the cosine of negative x. So basically we're going to take the reciprocal of that cosine business. But I'll write it out here. So you get 1 over the square root of 63 divided by 8. Okay, so that is just 8 over the square root of 63. Alright, moving forward, the cosecant of negative x equals 1 over the sine of negative x. And sine of negative x is negative 1/8, so this is 1 over negative 1/8. And so that makes negative 8. So notice, just as long as we figured out for sine and cosine what the behavior is, we were done right away. So can't emphasize it enough. Sine and cosine pretty much does all the tricks for you as long as you know those identities. So now here's where the fun begins. Determine the amplitude and period of the following functions. I have a little illustration here. So we have 5 sine of 3x. So what the heck is this doing? So if you look, I'm going to go back to a graph here. So what I have given in this graph is just the function y equals sine of x, right? And this a value is going to change, and that's going to be our amplitude. The b value is going to be what's changing our period. So I'll start with the a. What do you think is going to happen as we increase the value for a? Are there any guesses out there? Anyone want to take a guess as to what might happen if I increase this value of what would be happening with the value out in front of the sign? So if I multiplied sine by some number, so say instead of 1 I went to 2, what would happen? Any guesses? Are we going to get further away from the x-axis? Are we going to shrink down towards the x-axis? What's happening? This ties back in with your vertical stretches and compressions, and then your horizontal stretches and compressions, except now we have a periodic function. So notice in this graph, so 2 is the height right there. The normal amplitude of this thing is 1. So as I start to stretch this a value, you'll see the values, it'll show right here. So as I go up, what's happening with our curve? Well, it's starting to increase. So if I go all the way to say 3, or somewhere around 3, oh, get back there. Well, there we go. Notice when I go 3 sine of x, the amplitude has jumped to 3. Okay. So as we start to increase this a value, this thing starts to get higher and higher, further and further away from the x-axis. So that's what's happening with the amplitude. In terms of, and I can go all the way up, and I stopped this one at 4, but when you're looking at it, and on the other side of things, if I go all the way down to say 0.5, right? Notice I'm only at 1/2 is how high our wave is getting, right? So those are the main ideas when it comes to amplitude. So we have 1 right here. Now on the other end of things, so I'm going to start messing with the value inside the parentheses. So that's going to be more like a horizontal, either stretch or compression. If I get larger, what's going to happen? Well, remember, it does something funky when we do inside the function. Rather than what we thought would be a horizontal stretch, if we go by a factor larger than 1, it becomes a horizontal compression towards the x-axis. So our normal period, if you notice, I know the numbers are like 5 and stuff here, but it actually is 2 pi, and that comes from the unit circle. It takes full 2 pi for us to get all the way back around, right? So 2 pi is our period. So what's going to happen when we start doing this? Well, notice we're shrinking it down and down. So our period is getting shorter and shorter because we can get back to the original starting point and just have a repeat of the curve in a shorter distance. So at the end of the day, I think we go all the way to this 6.28, whatever the heck that might be. Okay, and we have something happen like that. Now on the other end of things, let's see if I put it in here. Oh, yeah, so it approximated us at this 0.63662. The actual value, you can't see it because it's kind of hidden up here, but it's 2 over pi is the actual value. And notice what happened to when we had 2 over pi. Where does our period go to? Well, it expands out quite a bit, right? So that's the idea, is in terms of what happens with this graph when we start messing with that. And 2 pi, when we plug that in, notice we are oscillating within a unit of 1 essentially, right? So how do we kind of work overall with these things in terms of our graph? Well, we have a normal amplitude, and then our normal period equals 2 pi. All right. So what does this 5 do? Well, that's a vertical stretch by a factor of 5. Okay. So that means if you have a vertical stretch by a factor of 5, we have a new amplitude. And we multiplied essentially our amplitude by 5. So our amplitude is equal to 5. And this 3x, so since we multiplied x by 3, this is a horizontal compression. Remember, it does just the opposite. So rather than multiplying by 3, so a horizontal compression by a factor of 1/3. So at the end of the day, that means our period, well, we've taken the 2 pi, and we multiplied by 1/3, or 2 pi over 3. Okay. Questions on that? It all comes down to just those transformations that we dealt with before, right? Another way you could do it is you can kind of figure out 3x usually equals 2 pi for the period, and then you go x equals 2 pi over 3 is your new period. Same thing. So in the second case, the same thing happens for cosine. The amplitude, if you don't believe me, I mean, you saw it just a second ago. I can bring it up and we can do the same thing. So if I change this to cosine, and then I'll change this a times b cosine of bx. Okay, so now we have a cosine function. Oh, okay, and kind of cool. You actually started off with this cosine function 0.5 cosine of 2x over pi, so it goes a little bit smoother that way. But you can see that it's even and all that jazz. I will actually start the a value at 1. Let you see what happens then from there. So if this is 1, and then if we start our b value at 1, so don't let the 1 point confuse you. Get rid of that. Okay. So now we started with cosine of x. You can see that function. Now if we're going to increase the number in front, same song and dance happens. The amplitude just gets higher, all the way up to 4. If we decrease it all the way down, it decreases just how we'd expect it to. Okay, so same thing as what happened to sine. Okay, so a normal amplitude though is 1, right? It's this distance from here to the top of the wave. Now with the B value, as we start to increase the inside, notice we're having our period, so that's the length it takes to get back to this peak. So boom, boom. Oh, whoa, that's even shorter now than what it was before when it was 1. And we can go, and it becomes even shorter as I bring it in smaller and smaller. And if I go and I take it out further, it takes a lot longer for me to get to the other peak. Right? So when I'm less than 1, it does this opposite. That's where when it's less than 1 and greater than 0, we're talking a horizontal, this case is a horizontal stretch. And then when it's greater than 1, it's going to be a horizontal compression. So this would be a horizontal compression by some factor of 1 divided by 2.5. So the negative, that's just a reflection over the x-axis, so that doesn't have an effect on the amplitude. But so this is talking a vertical stretch. By a factor of 7. So what does that mean? Well, that means our amplitude equals 7. And then on the other case, the period, this is a horizontal stretch. By a factor of, so it goes 1 divided by 1/3, which equals 3. So we got to multiply that 2 pi by 3. So you get your period equals 3 times 2 pi, which is the same thing as 6 pi. Okay, and if just in case you didn't believe me, I'll show you real quick. Once again, we'll pull up the graph. I think we had -7 cosine. So -7 cosine of x over 3, and I will go, it said to 6 pi, so I'll go from -6 pi to +6 pi, so we can kind of see what happens. Our plot range I'll have to adjust, and in order for me to get the whole graph, my claim is that we'll get from -7 to +7. So notice we're going to start with a valley there, and actually just to make sure, I'll change that to -7.5 and 7.5. Okay, a little bit better. So now you can see the graph fully. So if we start at this valley, notice we have to go all the way to the full out 6 pi in order to get back to the valley. Same thing over here. You start at -6 pi, you have to go all the way back to 0 to get back to that valley. So the period is in fact 6 pi, and then the amplitude being 7, you can kind of see right there's that cutoff for 7. So hopefully that makes sense on that part. If not, let me know. There's a box for you to ask questions. So let's go here. Oh. What's going on there? Alright. Woo! So now here we're talking. Evaluate the following inverse trig functions. So what is happening with these? Well, first off, let's go back to just cosine of x. So if I go back to cosine of x, and I go from -2 pi to +2 pi, and I draw this graph, and we'll make it -1.5 to 1.5 so we can see it nice and good. Notice this graph starts to repeat itself, right? And it's not one-to-one, so an inverse doesn't exist. So what we do is we restrict the domain. And where do we restrict the domain to? Well, we start looking along this curve until it starts to repeat. And once we get down to this valley right there, so right in that spot right along there, that's where we have repeats happen. And that point, in fact, is actually pi. So we start at 0 and we go to pi, and that's where we end up having repeats right after that. So what we do in terms of the fix is we restrict our domain. So the domain of this arc cosine is what it's called, is, whoops, not the domain, I'm sorry. The domain is actually -1 to 1. The range of arc cosine is 0 to pi. And the reason why, once again, is cosine looks something like this, right, to start. So if you have pi, if this is y equals cosine of x, everything after this starts to repeat one of the values between -1 and 1. So this is 1, this is -1. So what happens is we just say, okay, well, what we'll do is we'll restrict this domain, right, to 0 to pi of cosine of x. That means that's going to correspond to the range of arc cosine. Okay? So keep that in mind when we're working with these values. So evaluating the inverse trig function. So now we got to figure out, okay, what the heck if we're talking arc cosine equals -square root of 3 over 2. Well, that's where we need to do some work. So let's go back to the unit circle real quick. Well, not the unit circle, my apologies. Well, actually, yeah, we can work with the unit circle. So we're looking for something that has square root of 3 over 2 as the arc cosine value. So that means, remember that x equals cosine theta, and so you have -square root of 3 over 2 equals cosine theta. So that tells us that this angle must be between pi over 2 and pi. So we're so far so good. So that tells us a little bit of information. Now the rest, without a calculator, is what we're trying to do here. The rest we'll get from drawing a triangle. So let's see how we can do this. If I have a triangle and I want, think of cosine theta equals square root of 3 over 2. Let's not worry about the negative just for now. So if we put the square root of 3 over 2, if this is theta, right, square root of 3 would go right here, 2 would go right there, and then that means this is a 1. Now, moving forward from that point, let's see what happens. So square root of 3 over 2, and then what? We have a 1 over here, so that's the smaller of the angles. If you think about it, this is going to be a 30-degree angle, and this would be a 60-degree angle. Okay? So moving forward from there, what happens? Well, 30 degrees would have to be this reference angle right here. So we have 30 degrees sitting right there. Let me put that in. 30 degrees. Okay, so that's a reference angle. Now, that means that this must be 150 degrees. Okay, so we can convert that to radians to figure out our final answer. So you can either say one of two things. It depends if it's a degrees or radians. So 150 degrees, but I'd say more common would be converting that to radians. So 150 degrees times pi radians over 180 degrees. Notice both of those have a common factor of 30 degrees, or so you can divide both by 30, and you're left with just 5 pi over 6, which makes sense. The 30-degree angle is pi over 6, so you go pi minus pi over 6, and you're left with 5 pi over 6. So 5 pi over 6 radians. So pay attention to which answer it's looking for, but you can calculate both just by using those conversions. So for the arctangent of square root of 3, arctangent is a little bit different. So first off, let me go to tangent. I won't actually use Mathematica to draw that graph this time. Just want you to see it because it can generate them real quick. So this is y equals tangent of x. It has a whole bunch of repeats and so on and so forth. So you have pi over 2 and negative pi over 2 being your values for the tangent. If you have questions on how to generate the graph, you're more than welcome to ask. I can show you how this thing's generated too. You basically go off the unit circle, same song and dance. So in this case, what we can think of is this is our restricted domain. In the rest of the graph, and I'll put in the other pieces, you can put them in purple. It just basically repeats itself over and over again. But so what we do is restrict domain. So this is our restricted domain. Okay. So if that's our restricted domain, that means the range of arctangent of x, well, the range goes from, we'd never quite hit negative pi over 2 or pi over 2, so you have negative pi over 2 to pi over 2. Okay. And by the way, we can draw the graphs of these functions if you want to see those. It's pretty straightforward to do too. So now, same song and dance. We have to figure out what triangle will give us the tangent of theta being square root of 3. So the good news is, when you start to think about that in terms of the unit circle, this would occur if the tangent was negative. So this is negative values. But since we're positive, we're just from 0 to pi over 2. So we can just draw our triangle and we should be good to go. So tangent theta equals, well, let me actually write out the previous part. So arctangent of theta, or arctangent of square root of 3 equals theta. If you take a tangent of both sides, tangent of arctangent of square root of 3, they would cancel, and I have switched sides, but that means tangent of theta equals the square root of 3. Okay, that's all it is. It's just a fancy way of saying that. So we want to figure out theta. Well, the square root of 3 being over there, we can write that as square root of 3 over 1. So notice you have a triangle where you have theta, and that's opposite, which is square root of 3, over adjacent, which is 1. And then that means this is 2. Oh wait, this looks pretty familiar, doesn't it? The only difference now is the bigger angle is right here. So you have 60 degrees. So the way we're looking at this thing, this is just straightforward in terms of this is 60 degrees. Or if you wanted to convert it to radians, this is 60 degrees times pi radians over 180 degrees. So that makes pi over 3 radians. Okay, last but not least, you have the arcsecant. Now notice arcsecant, we have a negative. That's talking, this is 1 over cosine is the secant. So the same range is occurring here. You're talking from 0 to pi. Okay? Questions on, oh wait 1 second, did I botched that up? No, not 0 to pi. Arcsecant, so let's actually worry about that real quick. So for arcsecant, let's go over here. So arcsecant of negative square root of 2 equals theta. What does that mean in terms of what's going on here? So we have to first take the secant of both sides, and what would that mean? Well, we get negative square root of 2 equals secant of theta. Okay. So now, moving forward from here, we got to figure out what the heck would give us negative square root of 2 in terms of our triangle. An easier way for us to look at that's going to be square root of 2 over 1. Okay? So when we keep on moving on, what are we going to get? Also, we'll get theta sitting right here. Notice that makes a 1 a 1, and a square root of 2. And so the only difference, though, we need to get negative square root of 2 as our final answer. So that means one of the values has to be pretty much where we can't actually get to that value. So if you think about this, what's the actual range of this thing going to be? And so our possibilities are going to be the same as the arc cosine, with the lone exception being of when we're talking about 0, we're gonna, not 0, but 0 when this happens, this crossing 0, we're gonna run into problems. So you're gonna get a funky looking graph actually at the end of the day. But so what value would this be? Well, in terms of where this would occur on the unit circle, notice this is a 45-degree angle. So that means our reference angle would have to be over here, because that's where cosine's negative. So that's 45 degrees. So at the end of the day, what actually happens? Well, we're left with this thing would be 180 degrees minus 45 degrees, which is going to be just, what is that, 135 degrees, I believe. So you have 135 degrees. Now, moving forward into another version of that. So let's see, how can we write that as radians? We'll go 135 degrees times pi radians over 180 degrees. And so both of those have multiples of 45, so this would be 3 pi over 4 radians. And that should be our final answer in that one. Okay? Did we do that? We got that right. Yeah. Okay, good. Yeah, because our range should be, I'm just double checking to make sure. Yeah, when you think about it, our possible answers, we can't have pi over 2 as a possibility, but everything else is good. So we're good to go there. All right, so moving forward on that one. Yeah, this is always the tricky part, is double checking, make sure you're within the domain and range with all the inverse trig functions. So you got to remember your restrictions there. Okay, so moving forward on this, we want to list all asymptotes of the following functions. We have y equals tangent of x plus pi over 4, and then y equals cotangent of x. So a couple things that we might know or not know. I just talked about the fact that tangent of x has all these asymptotes occurring, and the graph looks something like this. So this is negative pi over 2, this is pi over 2. This is going to be 3 pi over 2. I could continue that trend in the other direction. This would be negative 3 pi over 2. Then I'd have 5 pi over 2, and so on and so forth. What's happening? Well, notice all the asymptotes. I can start at pi over 2. This is plus pi to get to 3 pi over 2. This is minus pi to get to negative pi over 2. This is minus 2 pi to get to negative 3 pi over 2. Notice I'm just adding multiples of pi all the time. So the asymptotes are at x equals pi over 2. Now there's another way. If you aren't sure on the graph where it's generated from, it comes from the unit circle. I'll be happy to show you that. But you can think about tangent is sine over cosine. So when is the cosine 0 is basically what we're looking at. Well, cosine 0 is, the cosine value is 0 at pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, so on and so forth. And you can also go negative pi over 2, negative 3 pi over 2, so on and so forth. So that's all we're doing, is we're figuring out when cosine is 0. But what this has done, so at x equals pi over 2 plus 2 pi k, or not 2 pi k, just pi k actually. Got a little ahead of myself. Where k is an integer. So what has this graph done? Well, it shifts left pi over 4 units. Okay. So what happens then? Well, so the asymptotes, if we shift left, we subtract. So it would be x equals pi over 2 minus pi over 4, right, because we shifted left, plus pi k, where k is an integer. So that means x equals this pi over 2 minus pi over 4. You can write this as 2 pi over 4. So this thing is just 2 pi over 4. 2 pi over 4 minus pi over 4 leaves us with 1 pi over 4. So pi over 4 plus pi k, where k is an integer. Okay, last but not least, I'm going to show you a different route for finding cotangent of x. Well, so if you want to find where the asymptotes are on that thing, let's write this in kind of what I was mentioning before. This is cosine of x over sine of x, right? So if you go back to the unit circle, remember, x equals cosine theta, the y equals sine of theta. And you have 0, pi over 2, pi, 3 pi over 2, and you could use a similar notion in the previous one, 2 pi. So here's the deal. When is this equal 0? All right? Well, it's when the y value equals 0 on this unit circle. Well, it's here and here, and all multiples of it. So you notice you go 0, pi, 2 pi, 3 pi, right? And then we go 4 pi, so on and so forth, right? So the asymptotes in this case, you actually have them right away. All right, x equals 0 plus 2 pi k, or sorry, I keep on putting 2 pi out of habit. It's pi times k, where k is an integer. Now that means if you had a list of these where it had 5 pi, 7 pi, and 3 pi over 2, you'd pick the 5 pi and the 7 pi because they fit this format, right? You could find integers such that that happens. So the 3 pi over 2 doesn't work because you'd have to multiply pi by 3 halves, and 3 halves is not an integer, so that wouldn't work in that case. But so that's how you can solve those. It's just basically repeating so many times around the circle. Any questions on that piece? Okay, we'll finish up. Evaluate the following. We have tangent of arctangent of 4/11. Well, the beautiful thing here is these two things are inverse functions. So since they're inverses, these things kind of cancel. The reason we can get away with that here is because we're talking positive, so there's nothing really to worry about. And so we get our answer very quickly, since these two match, is 4/11. Now, the other case, though, not as easy, right? So we have arc sine of 1/3. So if you have arc sine of 1/3, remember that equals theta. What does that mean? That means 1/3 equals sine of theta. And the beautiful thing here is we can make a triangle where you put theta on one side, you put that's opposite over hypotenuse, so you go 1 here and 3 here. So that means, remember, a squared plus b squared equals c squared. We're assuming a right triangle. So you get 1 squared plus b squared equals 3 squared. So b squared equals 8. that means this side is the square root of 8. Okay, so now we're ready for the cosine of this, which I'll replace with theta. Okay, cosine of theta, what does that equal? Well, it's the adjacent side, which is square root of 8, all over the hypotenuse, which is 3. Okay, so I don't see any questions left. If you all have questions, please feel free to email me. That's what I'm here for. And I'll be hosting another review session if you all have some more questions too. So just keep on asking them, and I'm happy to help as much as possible. Y'all have a good night.